All right, hello and welcome to week 2 of NTI. So we are looking at solving trig equations today, and it's going to involve a lot of the stuff that you remember from just solving algebra equations, as well as the trig things like, do you remember a unit circle? Do you remember what angle goes with which ratio? So let's start off with this first example. The main goal when solving a trig equation is to always isolate the variable. This is important to keep in mind because it'll give you a guiding point, kind of like a waypoint to look towards when you're solving. Now, this first example has two trig functions. They're the same trig function, sine, and I want to get those variables together, because if this equation looked like x plus radical 2 equals negative x, then we would know exactly what to do. We would combine the x's on one side and then we would solve. However, we have a sign in the way, so what we really ought to do is put our signs together and isolate our variable from there. So I'll have radical 2 equals negative 2 sine of x, because I subtracted this sign from each side. And then I can divide or manipulate everything that is next to my variable away from that variable. So I'm going to divide by negative 2, so I'll get radical 2 divided by negative 2 equals sine x. And at this point, we ought to know what x is. However, I want to use an inverse trig function just to show that's the operation I'm performing. I get radical 2 over 2 equals, what's the angle that goes with negative radical 2 over 2 for inverse sine. And you're thinking through, well, I have to answer an angle that's on this right half of the unit circle, if we remember that from our inverse trig unit, and that's got to be negative pi over 4. Cool, so x has to be negative pi over 4. If you said, wait, can it just be the, like 7 pi over 4? Then you'd be right, because that would actually solve our solution. If we look here, that's actually an angle that would satisfy this equation. Even though we used an inverse trig function over here to get an answer, doesn't mean 7 pi over 4 is incorrect and wouldn't solve our equation. The trickiness of solving a trig equation is an angle can be represented as an infinite amount of other angles. So what we need to do is we need to give a general solution to this problem, to this equation. So we know that one solution is negative pi over 4, and we can add or subtract 2 pi n to this angle to get any other solution. So yes, 7 pi over 4 does work, and then if we added another 8 pi over 4, we would get 15 pi over 4 working as well. Good. So you might receive a direction asking for the general solution or the solution on an interval. And I'll show you what the interval solution looks like in a second with our last example. So for this second example, I want to collect like terms and factor. So I'm going to kind of start off like how I did on the first one, and I want to get my cotangents together. Last time it was sine, now it looks to be cotangent. So I'm going to subtract cotangent x, and I'm going to set up a factoring situation. And it's really important one side is 0. So we can use the zero product property, which is why factoring is so nice. Because I couldn't solve something that has two separate variables. I know it looks strange, but this cotangent and that cotangent are separate, are solved separately than something that has a cosine in it. So it's important that we factor those things away from each other, the cotangent and the cosine squared. So if I factor cotangent away from everything, then I'll get a nice cosine squared x minus 2, and all that equals 0. And at this point, I can use that zero product property to set cotangent x equal to 0 and cosine squared x minus 2 equal to 0. Now, we just have to complete this with order of operations, and thinking about, well, where is this true on the unit circle? So cotangent x equals 0 when cosine is 0, and cosine is 0 when x equals pi over 2. And I know that cotangent is going to be pi over 2, so for my general solution, I know that x equals pi over 2 cotangent is going to be 0 at pi over 2 in a few different places. So how often does that happen? Well, it'll happen every pi n. So notice that my solution for cotangent is going to have a general solution that represents the period of cotangent as well. So solutions repeat every pi. A lot of stuff is being combined here for us. Now if we jump over here to the right side, I've got cosine squared x minus 2. Okay, I'll start off by isolating my variable. Okay, now remember this squared cosine, I need to square root that to get rid of the squared cosine, and I'll have a plus or minus radical 2. And I want to know, where is this x equal to, what angle gives me a cosine of plus or minus radical 2? Now, this might look suspicious because, well, I don't know an angle that goes with plus or minus radical 2. In fact, this is outside of the range of solutions for cosine, so this here is no solution. So that means our only general solution is what we found with cotangent of x. However, if we had a nice 2 over here on the right side to divide, we would get a nice pi over 4 and 3 pi over 4 solution. However, we don't. Okay, one thing I wanted to mention is wear a hat for one of the Zoom meetings this week if you attend one. And we'll keep it a secret for people who miss this in the video. Maybe they'll catch on. For this third example, the quadratic type, and to write as a single trig function, this equation has a lot going on with it. First thing I notice is it would be really difficult to factor this because, well, number one, cosine isn't the same as sine, so how can I factor something that doesn't have a common term? Also, it has 3 terms, so that's unfortunate. That means I have to find something that's in common for each of these 3 terms, or we could notice that the degree in the first one is 2 on x, degree is 1 here, and the degree is 0. So this looks like a quadratic equation. However, like I said, we have a problem where the cosine variable has to look like sine, or the sine variable has to look like cosine. Now it would be a lot easier to turn this sine squared x into cosine squared using trig identities. So I want to change sine squared into 1 minus cosine squared. And it might look a lot more complicated now, but let's continue to distribute and then maybe combine some terms here. And then I'm going to get rid of this negative because I don't like to see it. Cosine squared x minus 3 cosine x. And I'm just going to do that by multiplying both sides by -1. If I multiply 0 by -1, I still get 0. And okay, so that's gonna look a little bit better, but this is really tricky because this, and it's hard to notice, especially if you've never done this before, but now you know, this looks like a quadratic equation. The cosine variable acts like an x, so if this is just 2x, and it doesn't have to be an x, it could be any variable. If this is just 2x squared minus 3x plus 1, then you can use the quadratic formula, or better yet, you could just factor this. So how does this equation, if we rewrite it, so how does this rewritten form of the equation we already have factor? And then I'll just replace that x that I used to make this problem simpler with my cosine variable, and then I can use its zero product property to solve. So I've got 2 cosine x minus 1, and then cosine x minus 1 equals 0. Awesome. So now over here on the right side of the equation, or the right side of my page, I'll just write the rest of my solutions. So I'll have 2 cosine x minus 1 equals 0, and cosine x, minus 1 equals 0. Now I know that I'm using the general solution format because I was just asked to solve. So I want to make sure to do that to represent the general solution. So I'll have cosine x equals 1/2. Where is that true? And then I'll have cosine x equals 1. So where is that true? Over here on the top, x is equal to pi over 3. And x is equal to, where's cosine 1? When x is 0. So I want to represent my solutions as pi over 3. How often does cosine repeat? 2 pi n. And x is also equal to 0 plus or minus 2 pi n. Or just 2 pi n. So this would be our final answer to that crazy question, because we had to go through a lot just to get the variables to cooperate with us. Okay, this is our last example. So we want to find all solutions for everything on the interval 0 to 2 pi for this equation here hidden in the middle of all this. So we want to find all solutions from 0 to 2 pi. Now, this is a little strange because I can't isolate this. I can't be like I can't just move sine. I guess I could. I could isolate the one and I could put the trig functions together, but that doesn't really help me out because I've got like different trig functions. I can't just combine them and then get one variable. I want one variable. I'm isolating the variable. So that's not going to work out. Can't do that. I wish we could. So let's go ahead and square both sides. This is another trick, and you might be like, square both sides? What's going on with that? I want to do that so I can use trig identities to change sine and cosine into one or the other. So I'm squaring both sides. Alright, so I got cosine squared x plus, alright, how do you square a binomial? I got 2 of the middle term, 2 cosine x, plus the last term squared, and that equals sine squared x. So, okay, this is looking better. It looks like it would be problematic for me to change this, sorry, which do I want to point at? For me to change this cosine squared x into a sine squared x, or a 1 minus sine squared x, because then I'd still be left with a cosine variable that I couldn't change around. So I want to swap this sine squared x into 1 minus cosine squared x. So cosine squared x plus 2 cosine x plus 1 equals 1 minus cosine squared x. Yay! Now I have all of my variables as cosine, and I can combine like terms, and hopefully that puts me in a quadratic situation that I can factor. So I've got 2 cosine squared x if I add the right one over here to the left, and still have a 2 cosine x. And then if I subtract 1, then I'll have 0 over here. Now I can factor. Oh, cool. So this is even an easy one to factor. So I'll have cosine x plus 1 here, and all that equals 0. Alright, so now what is the solution to 2 cosine x equals 0? And what's the solution to cosine x plus 1 equals 0? So now I need my direction again. Am I writing a general solution? No, I'm just writing a solution on the interval. It's over here on the right side. A solution on the interval from 0 to 2 pi. So these are my two solutions. From 0 to 2 pi, pi over 2 is a solution, and pi is a solution. Awesome. So I'd like you to try these in your textbook. This is 396, page 396 in your textbook. It's numbers 7 through 16 and 21 through 34. Please be around for some practice on Zoom. I do expect to see you at least, I'm going to shave it down to at least once a week on Zoom. And then I will talk to you guys later. Bye.